So today's lesson is sort of an extension or a continuation of an idea that we stated yesterday. Yesterday we talked about combining functions, add, subtract, multiply, divide, composition. And the idea behind that is that functions are just like regular numbers. Anything you can do with regular numbers, we should be able to do with functions. And one of the things that we learned in primary school was opposites. And when you went through your, first grade math, second grade math, third grade math, hopefully your elementary school teacher taught you about opposites. Adding is the opposite of subtracting. Multiplying is the opposite of dividing, so on and so forth. So it sort of makes sense that if functions behave like numbers, they should have opposites or inverses as well. And indeed, that is the case here. So what's the idea? How do these things, which we call inverse functions, work? Well, to do that, we're going to have to go back to the idea of what a function is. Now, instead of analyzing the formal textbook definition of a function, I'd like to go take a look at this mapping diagram. Simply put, a function is a machine, right? It's a machine that takes things, in this case, since we're talking about math, it takes numbers from a group, which we call the domain, right? It takes whatever number you want, let's just say the number 2, and it transforms that number 2 into another number, and then that group of numbers, which we call the range. So let's pretend that f of x, this is just a random example, there's nothing special about it. F of x is 2x plus 1, right? So if I take a 2 from the domain, put it inside of the f function, this function here should transform that number 2 into a 5. That's basically that's basically the idea of a function. It's a machine, it's a thing that takes a number, does stuff to it, spits out another number. The group of numbers in which I take from is called the domain. The group in which I spit numbers out is what we call the range. Conceptually, an inverse should do the exact opposite. An inverse should undo everything a regular function does. So in this instance, whatever this inverse function is, it should take this 5 here and spit back out a 2. Now the notation for an inverse is a superscript -1. Right. Now let's use our terminology. The group in which you take numbers from is the domain. The group that you put numbers into is what we call the range. So for the regular f function, that's why I called the left the domain, because that's where I'm grabbing from, and that's why I called the right group the range, because that's where I'm putting it in. Now if you focus our attention on the inverse function, the yellow function, which group, the left or the right, am I grabbing from? The right group. So from the perspective of the inverse function, this is actually the inverse's domain. And from the perspective of the yellow function, the left circle is actually the range. This simple picture, I think, highlights one of the important relationships or the characteristics between a function and the inverse. So this is sort of like the big idea or the big picture. Notice the domain of the original function, the black domain, is the same group as the range of the inverse function, the yellow function, the yellow range. So the domains and ranges of a function and its inverse swap. That's the relationship between a function and inverse. All it does is it changes what the domain and range is. Specifically, it swaps them. Right. What are some implications? AKA, well, what's the definition of domain? It's the set of all x values. What's the definition of range? It's the set of all y values. So if the idea is that the domain and range flip-flop between a function and the inverses, domain are x's, y's are ranges. So then the idea is that the x's and y's swap. This one simple idea will allow us to achieve our 4 objectives today. As you guys can see on the agenda, we have 4 objectives. Can I evaluate inverse functions? Can I use the horizontal line test to determine if an inverse exists? Can I find the actual inverse equation? And lastly, can I sketch inverse functions? And all it is exploiting this relationship here, that between a function and its inverse, the domains and range flip-flop, the x's and y's flip-flop. Right. So what do I mean? What are some implications? Well, we know for a regular function, it's always y equals f of x. The function takes in x's and spits out y. That's exactly what this says. F of x, it takes in x's, equals y. It spits out y values. So its inverse, it should be the exact opposites. The x's and y's flip-flop. It should be the inverse function takes in y values and it spits out x values. This simple idea allows us to evaluate very easily. For example, suppose you had a function f, right? And you know what? I'm going to be mean. I'm not going to tell you what the equation is. I'm just going to tell you have some function f. But I'll throw you a bone, such that I will tell you f of 2 equals 5. Right? So I have this mysterious function. I'm not going to tell you the equation, but I do tell you that if you plug in a 2, you'll get out a 5. There are a lot of possibilities. It could be the 2x plus 1 that we did in the previous example. It could be x cubed minus 3. There's an infinite amount of answers, an infinite amount of functions where this is true. So this is a hard question. But I'm going to ask you this. Find f inverse of 5. I was actually lying to you. This is not a hard question. This is a rather trivial, straightforward question. So here's the idea. A regular function takes in x's, spits out y's. What is the connecting relationship? The inverse function takes in that y value and spits out x values. So because I told you this, f of 2 equals 5, I told you that the x value is 2 and the y value is 5. So all this question says is, hey, if you put the y value of 5 into the inverse, we expect it to give us back. That is the answer, 2, right? So this is a trivial example. Therefore, f of 2 equals 5. That implies that if I put the 5, the y value, into the inverse, I should get out of 2. We answered it. Easy peasy. We're done. That's it. That's it? That is it. That's just basically this question is testing you whether or not you understand the relationship between a function and its inverse. Of course, I can ask you this a bajillion different ways. I could give you function notation. I could give you a graph. I could give you a table, but the idea is the same. Inverse function takes in y values, spits out x values. Okie dokie? Okay. So I did say that everything you need to know about inverses is the first big idea, the x's and y's swap. What are some other things that I may ask you to do? I may ask you to verify whether or not an inverse exists. Before we do that, let's just do some quick vocab here. In the world of functions, there's this thing called one-to-oneness. Right? So the idea or the definition is a function is one-to-one. So that's the vocab word, one-to-one. If and only if it has an inverse. How can I easily tell if a function is one-to-one? How can I easily tell if a function is invertible? Well, we have a graphical test. We call it the horizontal line test. Yeah. Some of us may be familiar with the vertical line test. That is a test to see whether or not something is a function. The horizontal line test follows similar ideas, except instead of vertical lines, it's horizontal lines. The vertical line test states a graph is one-to-one if and only if any horizontal line intersects it at most one time. For example, this shape here on the left, let's say a sideways parabola, that function is technically one-to-one. A regular parabola is not one-to-one. Why is the left shape one-to-one? Because no matter what horizontal line I draw, that horizontal line, this horizontal line, that horizontal line, I can do this forever and ever and ever. Any horizontal line I draw will only cross the sideways parabola once. But if I did the same thing for a regular parabola, this horizontal line, crosses twice, it is not one-to-one. It is not invertible. Right? So horizontal line test is just the inverse equivalent of the vertical line test. Okay. We okay with that? Yeah. Of course, just saying it is one-to-one, I mean, that's great, that's easy, but okay, what is the equation? What is the inverse equation? That's the big question. Okay, so I give you a function. I know it's invertible, but what is it? How do I find it? Finding inverse functions. Right. And the technique is based upon that, again, that big idea at the beginning. An inverse function will just swap the x and y's. So that's what you literally do. Instead of focusing on the y's, we're going to focus on the x. We are going to solve for x, swap the x and y's, only if it's not a contextual problem. In other words, if it's not a word problem. If it is a word problem, you would not swap the x's and y's, right? But that's it. That's how you find an inverse function. Just solve for the other variables, and if it's just a regular x and y, swap them. The reason why we don't swap them if it's a word problem is because in a word problem, those letters mean something. T means time, V means volume, C means cost. It does not make sense to say magically cost becomes time, right? So when it comes to finding inverses of word problems, you just solve for the other variable and you're done. If it's just a generic y equals 2x plus 3, yeah, we'll go ahead and swap them. For example, suppose I asked you to find f inverse of x, find the inverse function, if the original function f of x equals, say, x minus 2 over x plus 3. So, okay, let's do that. Now, the first thing I would do is I would solve for x. Now, here's my suggestion to you. Doing algebra with function notation, that f of x, it's possible, but for me, it's personally annoying. So I would actually do a step 0. Change all the f of x's into y's. So I would do y equals x minus 2 over x plus 3. Now it's easier to solve for x. So think back to Unit 1. This is a fractional equation. One technique to solve a fractional equation is to get rid of the fraction, because I know how much you guys love fractions. So I'll go ahead and multiply both sides by the denominator. I'm going to multiply both sides by x plus 3. Is it okay if I do two steps at once? Can I distribute at the same time? So multiplying both sides by x plus 3 gives us xy plus 3y equals x minus 2. All I did was I distributed the y over. Now, Algebra 101. I'm focusing on solving for x. So to solve for a variable, bring all the variables you're solving for on one side, bring everything else onto the other. Since I'm focused on solving for x, I want to move this x to the left, so I'll subtract x from both sides. You guys notice how this 3y does not have an x? I don't care for him, so let's get rid of him by subtracting 3y. Yes, it does have a variable, It just doesn't have the variable that I want, so I don't care for it. Just get rid of them. Then that gives us xy minus x equals negative 2 minus 3y. So here are the x's that I want, right? So I have two terms that contain the variable that I want, but I can't combine them because they're not like terms. I need to extract the x out. The technique, whenever you have multiple terms, is to factor. And then last but not least, it should be very easy to solve for x now. Divide out that parentheses. X equals negative 2 minus 3y over y minus 1. Okay. For all intents and purposes, that is the inverse. That is the inverse relationship. It's not a word problem, so I'll go ahead and swap the x and y, because most equations, when you think of, hey, think of a function, 99.99% of mathematicians will tell you, oh, y equals. We typically don't do x equals. So we're going to swap the variables. All the x's become y's, all the y's become x's. X minus 1. So I would actually say, hey, this is the inverse equation. Right? That's not wrong. You submit that on the test on Friday, I'll give you full points. However, if I scroll up to the original instructions, the original instructions did say find f inverse of x. They just want to put it back in function notation. So the very, 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 very last thing I would do is I'd change this y into function notation. I would change that y into f inverse of x equals negative 2 minus 3x over x minus 1. This is the perfect answer I would submit. But again, if you get up to here and you forgot to do that, I'd still give you full points. But this is what I'm looking for. Not too bad? Yeah. It's just finding inverses. Very easy. It's just one idea. Swap the x's and y's. You may get funky problems that provide a domain restriction. So we'll do the same instructions. Find f inverse of x if f of x equals 1 over x squares. And they may tack on a domain restriction. Oh, by the way, x is less than or equal to 0. What does that less than or equal to 0 do? Oh my goodness, how does my problem change? I'll tell you this right now, don't worry about him. Pretend he doesn't exist. So we'll just go through the motions. And this one I'll solve a little bit faster because I think you guys get the idea. First thing I'll do is change the f of x into a y. Then I'll go ahead and solve it. So I'm going to get rid of the fraction, multiply by x squared. X squared equals 1. Divide out the y. X squared equals 1 over y. And to solve for x, to get rid of a square, we square root. But we are solving an equation. We are manipulating equations. So whenever you take a square root, your answer will be plus or minus. Right. Then the last thing I want to do, since it's not a word problem, swap the variables. Y equals plus or minus 1 over radical x. And then the instruction said find f inverse. So I'm going to put it in function notation. F inverse of x equals plus or minus 1 over radical x. So far, that's pretty straightforward. I didn't do anything too crazy. It's just algebra. However, checking the answer key, looking at the solutions guide, this right here is not the right answer. You would not get full credit on it if this is a quiz or a test, because I have two functions here. F inverse of x equals the positive and f inverse of x equals the negative. By definition, I should only have one. That's what it means to be a function, right? One output. So, which one's the right answer? You take a look at the original domain restriction and remember what the big idea was. I'm going to scroll all the way up, but I'll scroll back down. The main idea of inverses is that the domains and range swap. So, I know at the very beginning of this problem, they restricted my domains. My domain is less than or equal to 0. Those are negative numbers. Well, I know that if the domain of the original has to be negative, then the range of the inverse also has to be negative. So that just simply means you keep the negative answer, not the positive. That is the inverse of the original function. Questions, comments, concerns? Alrighty. the last thing inverses can do is help us sketch. So a question that you might see on a quiz test, or you'll definitely see on the assignment, is sketch the inverse of the function shown. Right? So they're not going to give you an equation, but rather they're going to give you a picture and ask you to invert it. How would we do that? Suppose they gave you this picture. Now, since we're drawing it ourselves on our notes, I'm not going to make it too complicated. Let's just do a simple line. So, I don't know, make a relatively large coordinate system, maybe an 8x8, 7x7, whatever, something along those, in that neighborhood. Right. And suppose that the picture they gave you was this. A y-intercept of -1 and a slope of, say, up 1 over 3. So up 1 over 3, up 1 over 3. And I could go the opposite way. Down 1, left 3, down 1, left 3, right? So suppose they gave you this graph. It's a line that has a y-intercept of -1 and a slope of 1/3. Not perfect, but close enough. All right. And I wanted to graph the inverse. Well, one way to do it is to go back to Unit 1. I give you a picture. Can you guys come up with an equation of this line? Y equals mx plus b. What is the slope? 1/3 x. What is the y-intercept? -1. Hey, with this graph, I can come up with the equation, and then we can do the previous example. Find the inverse function. But, that's tedious. What if I didn't give you a simple line? What if I gave you a crazy quadratic or crazy cubic? Coming up with this original equation is hard. So how in the world am I supposed to sketch the inverse without having the equation? Well, we're just going to use the big idea. The relationship between a function and the inverse is that the x's and y's, they literally just swap. So if I give you a graph, we should be able to read a couple of nice points. This point here is what? -6, -3. This point right here is -3, -2. This point here is 0, -1. This point here is 3, 0. This point here is 6, 1, right? Those are just nice, easy points I can read. Well, if the idea is that the x's and y's flip-flop, let's go from left to right. What is the inverse of this point? Well, if every single point is x, y, and I know the inverse just swaps the x's and y's, I expect the inverse will have -3, -6. So I can graph that, -3, -6. 1, 2, 3, 4, 5, 6. I know for a fact, it's not a guesswork. I know for a fact -3, -6 is on the inverse function. If -3, -2 is on the original function, I know for a fact that -2, -3 is on the inverse function. If I know that 0, 1 is on the original function, I can guarantee that 1, 0, or excuse me, -1, 0. Oopsies. There we go. -1, 0 is a point on the inverse function. If 3, 0 is on the original function, I can guarantee you that 0, 3 is a point. And then lastly, 1, 6. So does everyone understand what we're doing here? Like, since the definition of an inverse is a relation where the x's and y's swap, all I did was I took these points that we could easily read, and you literally just swap them, right? Easy peasy? All right. And then all that's left to do is connect the points. My tick marks aren't perfect, but close enough. Right. Now that's an interesting shape there. It looks like they're sort of mirror images of each other. I'm going to draw one more line, right? So the black was the original function, f of x. The yellow was the inverse function, f inverse of x. I'm going to draw one more line here. And what I'm going to do is I'm going to try to draw the axis of symmetry. What line would split this image down the middle? Well, it's not going to be perpendicular because it's not 90 degrees. But it is a line that's right between the axes. This line happens to be, if I had a better coordinate system, y equals x. And this is not by accident. It is not by accident that a function and its inverse are reflected over each other about the line y equals x. Because what does this equation literally says? The y value becomes the x value, which is the idea of an inverse. So of course the inverse function will be a reflection across the line y equals x, because that's how we find inverses. You change all the x's into y's and vice versa. So using that idea, we should be able to sketch inverses without needing the equation. I don't need to do all this work to find the equation. Just take a couple of points, invert the y's and the x's, and then you have the graph. Questions, comments, concerns? That's all we need to know about inverses. The ultimate idea, it's a function that cancels out another function. Conceptually, how do we create this function? Just swap the x's and y's. So by the end of today, we should be able to evaluate inverse functions, sketch inverse functions, find inverse functions, and read inverse functions. That is 2.8.